My name is Thomas Molgaard. I'm the Director of Software Marketing from the Systems and Software Group at ARM in Cambridge. We're based in Cambridge, UK. And the next 30 minutes are about the ARM Virtualization Extensions. So I realize that this is a little bit of false marketing because, you didn't come here to hear about marketing. But Marc, who I'm sharing the stage with, was kind enough to let me say a couple of words about the ecosystem before I hand over to him, where he can do a much more technical deep dive than me. So first of all, thanks to the Zen project for having us here. And also thanks to the Linux Foundation as well. It's good to see some recognizable faces here. So I'm just going to spend a couple of minutes talking about the ARM ecosystem and where virtualization fits in there. And then I'm going to hand over to Marc. Limited amount of time. If you've got questions, it will be around for the rest of today and for the rest of the week, so feel free to grab a hold of us whenever you see us if you have any questions. Right. So just very quickly about ARM, just in case someone in here doesn't really know exactly what we do and why we do it. So we do R&D outsourcing for semiconductor companies, meaning we don't actually produce anything that you can touch and feel. As such, we generate an architecture, we generate the associated IP, and then we license that to a wide variety of partners that are all part of the ARM ecosystem. A lot of you guys in this room are also part of that ecosystem. So we have an upfront license fee, so that means that's a one-time fee that you pay in order to license our IP from us, and then there's a royalty-based business part of that as well. So for every piece, for every product that ships with something ARM-based in it, we get a tiny, tiny share of that one. Very quickly, just around the segments that we are currently in, this one is, keep this one in mind, because as I go through the slides moving forward, there's a little bit of method to the madness. You predominantly probably know us from mobile phones. The vast majority of the mobile phones in your pockets right now are likely running on something ARM-based. So mobile computing is definitely one of the really big areas that we're in. We're moving into smart cities as well. So these are all about your intelligent street lights and all these different initiatives that can help you, or that can help cities lower the cost of them to actually run the infrastructure of a city. Secure payments is something that we're in. Consumer electronics, your television, your camera, your wearables, and so forth. Industrial, so we have a range of real-time processors or processor designs that are in there. So these are all from your robots in your factories and so forth that we're in. Automotive is something that we're increasingly seeing our architecture and our products being used in. And then finally, enterprise. So by enterprise, I mean server and networking predominantly, which is very likely to be what most of you guys in the room today are interested in. So without going into detail with what's in the blue boxes, probably because you might not even be able to read it, why should you care about virtualization on ARM? And if you think about the previous slide about the different areas that we're in, it's actually, it's a quite interesting approach. If you look at the scalability that the ARM architecture actually offers, we talked about before that we're in everything from your smartwatch to your big server, basically. And virtualization is actually supported across the range there. So that does open some quite interesting new possibilities for virtualization and some new use cases, because you can actually talk about, are there things out there that we haven't really thought about yet, right? So I'll get back to a little bit more about that, but one of the ideas here is, does it make sense to migrate a VM that runs on your phone or on your smartwatch to your workstation, or maybe into the cloud, right? So there's some sort of interesting things to think about here if you consider all of the places where the ARM architecture is represented. So what is it that we do? As we said before, we don't actually produce something. We don't have factories where we produce our CPUs or cores. But what we do from the software enablement perspective is, if you look at the inverted triangle here and you look at the blue arrows and the green arrow on the side, we play a quite active part in enabling our architecture and our IP, but we don't enable it all the way to the top. So the numbers you see, tens, hundreds, thousands, and hundreds of thousands, those are the active players in those spaces. Right? So if you look at tools or models, you've got the number of companies or vendors that are active in that space are in the tens. As we move up and look at who's actually active in supplying drivers, who's active in OSs, it's in the hundreds. But then when we get into middleware and we have thousands of different companies that are active in there, that's where we taper off our direct engagement, because actually working directly with every single one of those players in there becomes quite challenging for us. And obviously when we get into the application space, if you think about the Google Play Store, us having a direct engagement with every single app vendor in there is not really an option. And the green arrow on the right indicates where the actual partnership or the ecosystem then goes in and takes over. So that's where a lot of the work is happening. In the background behind the blue arrow, there's sort of a lighter blue arrow that shows what we aspire to do. So we recognize that moving forward, as we move into new areas, there is an increased demand for us to get involved in things like middleware. So this is sort of the aspirational blue arrow of what we will be investing in moving forward, putting more resources in on that. A number of you may have heard about Linaro. So the Linaro is the Linux on ARM organization. So this is a big collaborative framework for a number of companies that invest in Linux running on various versions of the ARM architecture and IP. So we do a lot of work together with Linaro. It is a very, very good collaboration environment, so I'll be mentioning that. The next slide, I'm going to skip through it. It is essentially it's translating the previous slide into something a bit more tangible. I'm sure these slides are going to be available to you afterwards, but this is essentially the previous slide, just showing some of the various things that you probably recognize, including on the top stack, anything open in front of it. So I'm going to rush through that one and get to my last slide before I hand over to Marc. We are committed to a vibrant ecosystem. I think that's pretty obvious if you sort of understand the way that our business model actually works. And we think that the Zen project is a damn good example of that. We're happy to be here. The reason that there's a picture of a slightly confused version of myself up there is that we have, as a member of the Zen Project Advisory Board, we have been participating in some of the marketing activities that Lars was mentioning earlier, and I was lucky enough to front that one and talk about Zen on ARM. Also, welcome to Alibaba. I don't know if the representatives from Alibaba are actually in the room now, but it's great to have you guys on board in our project. And then basically the call to arms part in here is, I referenced earlier on the slides that there are new possibilities for virtualizations and there are possibilities for new use cases. So this is sort of us sort of challenging you guys or encouraging you guys to work with us, exploring some of these new use cases that the architecture actually could offer across these various segments. Right, on that note, I'm going to hand over to Marc Zyngier.
Hello, everybody. So, as it says here, I'm Marc Zyngier. Who am I? I'm a fairly long-time kernel hacker. For those who've played with the MD driver, I'm the original author. If it corrupts your data, don't blame me. I've been with ARM for the past 5 years or so, as part of a very small team of really, really good engineers. So I'm the idiot of that group. That's why they send me to conferences. And we're basically focused on architecture and IP enablement. We don't do drivers, really. We don't do Userspace at all. We are really, really focused on making sure the architecture is really well supported on Linux. So I'm personally looking after virtualization and anything having to do with interrupts. I'm also maintaining the kernel's RQ chip and RQ domain subsystems. I co-maintain KVM ARM. Don't throw anything at me. I do that with Christopher Dahl in Linaro, a really, really good guy. So why KVM? It allows us to focus on one single project. As I said before, we're a very small team. We can't really afford to deal with too many things at the same time. So Linux for us is a very good way to prototype the architecture. Whenever an architect has some wacky idea of what we could do, we can prototype it on a single code base. That's really good. Yeah. But okay, why is Zen important to ARM? Like Thomas said, we have a very, very diverse ecosystem. And tons of very, sometimes conflicting requirements coming from partners that covers all the angle of virtualization. And then the idea of that one size fits all is usually a bad idea. I mean, monoculture, it's basically death. So having different approaches to the same problem is usually a good thing. And also, it exercises the architecture, which is what I really care about, in different ways. ARM doesn't directly contribute to Zen just yet. That could change quite quickly, but there's a number of indirect contribution. We've seen code from the Linux code base being ported quite nicely, actually, to the Zen kernel. Things like IOMMU support, interrupt controllers. And we have a very good relationship with the Zen hackers. We usually hash things over IRC or in that kind of settings, which is usually quite good. So, I'm rushing a bit, sorry. The ARM architecture itself, it's moved very, very quickly over the past few years. We went from quite dumb cores, ARM v6 type of thing, so that's late 90s, early 2000, to slightly more powerful cores, ARM v7A, so Cortex F5, A8, A9. But that's not really interesting. What's really interesting is on your right is stuff that knows about virtualization. So V stands for Virtualization Extensions. So Cortex S7, F15, S17, which you can find, in a number of products, boards, whatever. There's a Samsung smartwatch using a dual S7. You can run KVM or Zen on that. That's quite interesting. Find that really cool. And then there's the ARM v8 profile. So F53, F57, F52, S72, sorry. And that's just the cores that ARM produces. So how to read that? I should have started with it. ARM v blah A is the revision of the architecture, and Cortex something is an actual implementation of it. So that's sometimes a bit confusing, people confusing ARM 9 with ARM v9, which doesn't exist. All kind of interesting complexity. The good thing is, not only ARM produces ARM CPUs, yes, so processors that comply to the ARM architecture. So some of you may have heard of Applied Micro. They have a core called, or processor called XGene, Caviar-Mask, ThunderX. These are different implementations of the same architecture, and they are entirely compatible with the same code base. So, more technical. So that's the ARM v8 privilege model. So, from the top, which is basically Userspace, to the bottom, which is what we call the secure mode. We have 4 different layers. So EL0, that's Userspace. EL1, that's basically your kernel, your operating system kernel. EL2, that's where your hypervisor is going to be. It has a higher privilege than EL1. EL3 is what we call the secure mode. We have these 2 sides of the architecture, one non-secure, one secure, where you can have some firmware running in secure mode, doing some horrible key management or DRM, and we don't want to hear about that. We're only focused here on the non-secure side, which is where your hypervisor is going to run. So oddly enough, there is a higher privilege level than your hypervisor. Secure mode has control on your hypervisor. It can lead to all kinds of interesting things. So this supports both ER32 and ER64. So these are the names for the execution modes. We can switch from 32 to 64 bits only on an exception level boundary. You can't execute 32-bit mode and then switch seamlessly to 64-bit. That's not allowed. You have to go to a higher exception level, more privileged exception level, and gently ask, oh, please, can you switch me to this other mode? And the other guy says yes or no. AR64 always has a higher privilege level than AR32. You can't have a 32-bit hypervisor controlling a 64-bit kernel. That's not legal. It's always the other way around. Also, your 32-bit state is only a subset of your 64-bit state. That doesn't sound like much, but when you write a 64-bit hypervisor, if you save your whole 64-bit state, well, you have the whole state, including the state of a 32-bit machine. That's quite cool. You just have to cater for the 64-bit case, and you're basically done when it comes to support 32-bit guests. So what do we have in these virtualization extensions? So first, they come with basically the latest revision of the ARMv7 architecture. So there's this new ER2 or hype mode, which, as I said before, runs in non-secure mode, higher privilege than EL1. It gives you what we call second stage translation. So that's your nested page tables, EPT on the Intel world. It's nothing new, nothing fancy. It's an extra level of indirection between your guest and the physical pages. We have TLBs that are tagged by virtual machine ID, so that you don't have to blast all the TLBs in one go when you context switch. You can, if you really, basically you never have to invalidate TLBs unless you are making destructive operations on your page tables. If you're removing a page from your page tables, then you have to do a TLBI. Otherwise, you don't. You can trap most system registers. There's a rather fine-grained mechanism to define what you want to trap. You can handle interrupts. FRQs are a special kind of interrupt. It's a historic thing, but basically, they were supposed to be fast interrupt, not fast anymore. But that's a different kind of interrupt. And of course, you can route that directly to your hypervisor. The guest doesn't see a thing. And then the guest can have power virtualized services. We have an instruction for that. And most of the standard devices, interrupt controller, timers, are virtualization aware. Going to develop that a bit. So EL2, that's the mode where we run the hypervisor. So Zen or the world switch for KVM is going to run at that level. It's a bit weird. It's not a strict superset of EL1 where your kernel runs. It's actually a completely orthogonal mode. It really allows the sharing of the levels below, of the levels up of lesser privilege. It has its own translation regime, so it has its own set of page tables, only one level. You don't need two levels of page tables for the hypervisor itself. The page format is basically what we have for the for the other guests or even second stage translation. Has only one register to hold the page tables. That has an interesting effect, is that we can't run standard Linux at that level. We need two of these registers, one for Userspace, one for the kernel. So this ER2 mode is effectively a world switch. Either you run your entire hypervisor at that level, and that's fine, that's what Zen does, or you end up with a slightly twisted way of doing things for KVM, which basically considers the host as a specialized guest. So it looks like this. Your hypervisor switches the state. So that's your stage 2 page tables, trap configuration, general purpose register, system control registers, floating point if you're not doing it lazily, interrupt configuration, and timers. So that's the generic way, and on Zen, that's what it looks like. So on the left side, you see DOM0, which is with its kernel and its user space, and then the various DOM-Us, basically the same thing. With KVM, it's slightly more complicated. because, as I said, we can't run Linux all the way up. So we have this little box KVM here that is playing tricks and controlling the way the switching code works. But overall, the architecture gives you one way to implement a hypervisor, and then there's not that much difference between Zen and KVM in the way they are implemented on ARM. So an interesting thing on most hypervisor is how do you deal with VM exits? How do you preempt a VM? So we have a number of key events. Getting a physical interrupt. So apart from one particular case where I come to later, all the interrupts are taken directly to the hypervisor. The guest doesn't see them, ever. So they are forwarded to the hypervisor, who either deals with that at its own level, or then forwards that back to, for example, DOM0 for handling. Any form of stage 2 fault, for access fault, page fault, transition fault, that's handled as well at ER2. Well, at least that's taken at ER2. You can, after that, offload that to another level. Hypercalls, of course. So I've briefly talked about this secure versus non-secure duality. If a guest does an SMC instruction to do a secure call, so for example, oh, give me the key to decrypt that kind of file, or please decrypt that buffer, the hypervisor can act as a proxy and then forward it or implement something on the behalf of the guest. Wait for interrupt. That's basically what it says on the tin. You can trap that. If a guest decides to go to sleep until an interrupt fires, well, for the hypervisor, it's a good sign that the CPU is better used for something else, and we can put that vCPU on the back burner and go and do something else with it. WFE, that's another interesting instruction. That's wait for event. With that, it's a very good primitive to implement things like PLE. We don't have the concept of PLE by itself, because we are very much a RISC architecture, and PLE is a very high-level concept. But we can build something that's very equivalent to PLE with WFE. So when you have a blocking spin lock, and you know for sure it's going to block, we can trap that and do directed yield. It's quite efficient. Actually, if you don't do that, it's likely that if you seriously overcommitting your system, your host, you'll be in major troubles. And also, we can trap on a few privileged system registers and operations. If you have any questions at any time, please hold it for later. I'm trying to rush. Memory management. We have many page tables, way too many. We have 4K, we have 64K, and we also have 16K that not everybody implements. So 4K, that's everybody knows about that. It's just like everyone else, apart from Alpha. 64K, that's a bit of a novelty for most people. It's really big. Some people do love it. If you're doing databases, 64K pages, that's fantastic. Very little pressure on your TLBs. For everyone else, it's a nightmare. It fragments memory like hell. Everything's too big. More importantly, they give you interesting sections. So for 4K, 2 meg, for 16K, 32 meg, for 64K, half a gig. That's really cool. In 4 section, you have your 2 gig VM. I mean, that's again very, very light on your TLBs, and you can have something that's quite efficient. So how does it work? The guest is in complete control of its page tables. We basically don't want to know anything about it. Does whatever it wants, good for him. any page tables, just like on a bare metal system. That can be AR32, AR64, different page table format, whatever. And no shadow page table. Thank you very much. The hypervisor control the stage 2. As I said, TLB stacked by vMid, which on ARMv7 and ARMv8 are 8-bit. So that's 2056 VMs running concurrently. And I insist on the concurrently. They really have to be on one physical CPU at the same time before you run into any problem. So apparently for some people that's just not enough, but yeah. So when you reuse vMid, you have to issue a TLB invalidate. So yeah, that's not very often. So you can easily map a device into a guest space. You just put it into stage 2. And if you want to implement virtual devices, well, it's also very simple. You just don't put anything at stage 2, and you handle the resulting fault when you get an access, and you're going to emulate it. I mean, nothing of that is really new. But yeah, it just works. Interrupts. So we have the infamous GIC, as in generic interrupt controller. The only thing generic about it is the name. So like I said, we forward interrupts to the hypervisor, and it's the hypervisor duty to deliver to the guest. So that can be a wired interrupt or an MSI. We have assisted virtual interrupt delivery, which means we're going to queue the interrupt into some special register, and whenever the guest sees that, it's going to take it, and that's the whole interrupt flow is almost entirely handled in hardware. There's actually very little intervention of the hypervisor when it comes to queuing interrupts. The whole flow then is handled by the hardware. That can be either memory mapped or triggered by system registers for GigV3. So the hypervisor itself is going to deal with the relative priorities of the interrupt, if you're using priorities. Linux doesn't, so it makes it simpler. And you can also have a slightly optimized flow if you want to enqueue what is effectively the result of a hardware interrupt into a guest. We are able to do a trapless EOI. So normally, especially if you have level interrupts, you have to trap the EOI so that you can re-inject an interrupt if the line is still high. There's all kind of complicated logic if you're basically emulating what the hardware would normally do. With this system, we can at least not trap the EOI. If there was going to be able to automatically deactivate the interrupt, and if it's still pending, well, it will fire again. That makes it slightly cheaper. So that's not completely obvious, but that actually constrains the size of the VM. So GigV2, which is slightly ancient by today's standards, gives you a maximum of 8 vCPUs per VM, because IPIs, the register describing an IPI can only address 8 vCPUs. That's the reason why. Otherwise, we could do a lot more. But if you come up with a non-standard way of doing IPIs, you can have GigV2-like systems with more than 8 vCPUs. And I know some people have done that. It's really horrible, but they've done that. I won't name anyone. GigV3 gives you really a shitload of virtual CPU. I mean, it's really 4 billion vCPUs. Who needs that? I don't know. But more interestingly, it gives you device isolation. You can make sure that a device won't masquerade another one and issue an MSI. Some people like that a lot. And actually, if you look at the Intel IOMMU, that's what interrupt remapping is all about. It's about ensuring device isolation. And then we have GigV4, which is a really complicated part of the architecture. But that allows direct injection of MSIs into a guest without any intervention of the hypervisor. Yeah, so that's good. I'm not sure if it's really, really useful. It means if you want that to be useful, you need to pin your VM to vCPUs, to physical CPUs, and make sure they are never put away from that physical CPU. I assume it's useful in some cases. Timers. So timers is probably one of the hardest things to virtualize. So how does it work? We have a global counter observable by every CPU. So because there's one global counter, we don't have to synchronize anything. It's constant, always the same frequency, and always on. That's quite good. If you do power management, you guarantee that that counter will continue ticking. So we have a view to this counter from the hypervisor. Your guest also has a view on it. Actually, it has two. One we call physical, which is the same as ER2, same numbers. And then a virtual one, which has a per CPU offset, which is subtracted from the physical value. We're going to see that it's actually quite interesting what we can do with that. ER2 has its own timer. EL1 has two timers, one based on the physical count, one based on the virtual count. And what we can do with that, if you migrate a VM, migrating is going to take time. With that vCPU offset, you can basically make time contiguous. You're going to say, okay, it's taken me 10 seconds to migrate from system A to system B. That's fine. I'm going to set my virtual offset to 10 seconds, and automatically time becomes contiguous. It's quite nice. But you can also do something else with it. You can use it for still time accounting. Your vCPU has not run for that period of time. That's fine. You just accumulate it in the offset and use it to expose to the guest how much time you've lost. So that depends on how you want to implement it, what you want to expose to the guest. All that is basically free to be used. IOMMUs, favorite subject. We have, like most things, several revisions of the architecture. We have SMMU v2 and SMMU v3. We're not talking about SMMU v1 because it doesn't support virtualization. Support the same page sizes as the CPU, so a lot of them. Secure, non-secure devices. As I said, we don't have interrupt remapping because that's actually taken care of by the interrupt controller itself. SMMU v3 gives you number of improvement on SMMU v2, larger number of devices because all the descriptors are memory-based instead of SMMU v3, which has everything in registers. So things in registers, not that many of them, not that many devices. Or plenty of devices, but sharing the same page tables. Not necessarily a good thing. Also has support for ATS and PRI. Things I hate. Firmware. Really. So x86 has this notion of a standard platform. On every x86 board in the world, you'll find a number of I/O ports at this location. You'll find a bloody VGA device at this other location. Everything is the same. 3 minutes, that's plenty. that's that many slides I can skip. So on ARM, we don't have that luxury. Everybody does their own thing. They place things at random places in the memory map. You know, everybody comes up with their own IP. They are specific to their own market. They don't coordinate with each other. So instead of saying, this is bad, don't do that, we have another approach. We say, well, if you're doing that, at least make it discoverable in a way. And for us, firmware is the way to expose the system topology. So we have device tree. So It's inspired by open firmware in some ways, and it's very, very, very much dumbed down. I would have loved real open firmware, but we don't have that. So it's quite contrary to what people are saying. It's a fairly mature and robust solution. And it's been used on PowerPC for ages, and it works really well. It's really, really flexible. I mean, you can turn it in any shape or form you want. You can always do something with DT. And the most complicated platform you can imagine, yes, you make up the binding, you'll be able to use it. Yeah, there isn't any standardization. I mean, everybody invents new bindings all the time, and it's really, really hard to capture that and to make sure it's done in a sensible way. And it scares the x86 people like hell. And that's why we also have a CPI. Yes, it's basically a simplified version of the x86 thing. It's been merged with ARM64 4.1. I'm out of time, I know. It's really inflexible, but it gives us a more standardized platform. It's community driven, I'm not sure that's a quality, and it scares everyone else but the x86 guys. Can't please everyone. So we have evolutions to ARM v8. So we have new instructions, ARM v8.1, which has been announced at the beginning of the year. New instruction, new SIMD stuff, new memory management, bigger VMID. You can have 16K worth of VMIDs. Are you ever going to have that many CPUs in your system? And we have extension for Type 2 hypervisors that gives you basically the capability to run Linux in ER2. KVM is quite happy with that. Except I've had to rewrite most of the world switch for that. But the last line is interesting. That could be useful to Zen too, because you're able all of a sudden to have two set of page tables at the hypervisor level. I don't know yet how to use it for Zen, but I'm sure we can find good use for that. So maybe something around power management. So in conclusion, the ARM architecture is really a great architecture for virtualization. And it's not just about CPU virtualization. It's about virtualizing the whole system. It's scalable. We can range from IoT type devices to biggish servers. It's an open architecture. We have a diversity of implementation of solutions. It's also an architecture that evolves. It's not stuck yet. It evolves as good. And it's also a good architecture for Zen. It's been designed with Zen in mind. And yeah, the Zen kernel hackers have done really, really a good job. So Ian, Stefano, and Julia really deserves your applause. That said, thank you.